Today's lesson is on the laws of logic. Logic is a learned mathematical skill, a method of ferreting out truth using specific steps and formal structures. Some of those structures of formal logic are converse, inverse, contrapositive, and counterexample statements. Logical statements can be tested for truth or falsity. The phrase, "Jennifer's white birds," is not a logical statement because it lacks meaning. The phrase, "Jennifer is best at magic," is not logical because it is an opinion. It is not testable. The phrase, "Jennifer wears dresses every Tuesday," is logical because it can be tested. Either she wears dresses on Tuesdays or she does not. Logical statements must be tested to be valid. For example, of these two statements, one is logical in that it can be tested for its truthfulness. The other is an opinion, which cannot be tested for truthfulness. The first statement is an opinion and is neither logical nor factual. It cannot be tested to be true. We know the second statement can be tested for its truthfulness. The second statement is logical, but not factual. Let's look at a few more examples. Which of these phrases is a logical statement? Remember, it need not be true, just testable. Statements 2 and 4 are logical statements. Statement 1 is an opinion, and Statement 3 is a fragment with no logical meaning. 4 testable types of logical statements are converse, inverse, contrapositive, and counterexample statements. They can produce logical equivalents for the original statement, but they do not necessarily produce logical equivalents. Suppose that instead of writing an opinion for our first statement and a logical but not factual second statement, we wrote these two statements. We can use these statements to form a conditional statement with a hypothesis and a conclusion. If Jennifer is alive, then Jennifer eats food. This type of if-then statement is the heart of logic. We can immediately see that two statements result in a true conditional statement. Here is Jennifer. She is alive. She eats food. A logical equivalence recasts the same hypothesis and conclusion as a negative statement that produces the same result. If Jennifer does not eat food, then Jennifer is not alive. These statements have logical equivalence because they contain the same content and arrive at the same result. Statements with logical equivalence are either both true or both false. Let's look again at our original conditional statement. Switching the hypothesis for the conclusion provides the converse statement. If Jennifer eats food, then Jennifer is alive. We have the same words, but the order of the two parts has changed. In this case, the statement is still true, but it would not have to be true. Switching the conclusion for the hypothesis does not automatically prove the logical conditional statement, so the converse statement could be true or false. A logical inverse statement negates both the hypothesis and the conclusion. Again, here we have our original conditional statement. By carefully making the hypothesis negative and then negating the conclusion, we create the inverse statement. If Jennifer does not eat food, then Jennifer is not alive. The inverse statement may or may not be true. Let's compare the converse and inverse statements to see if we can make any judgments about them. It turns out that both produce true statements. Neither would have to produce a true statement, but in this case they did. It is not possible for one to produce a true statement and the other to produce a false statement. Now we know 3 facts about converse and inverse statements. If one is true, the other statement is true. If one statement is false, the other is false. And converse and inverse statements are logically equivalent to one another. If the converse reverses a statement and the inverse negates it, could we do both? Could we flip and negate the statement? Here is our original conditional statement again. To create the logical contrapositive statement, we negate the hypothesis and the conclusion, and then we also switch them to get, If Jennifer does not eat food, then Jennifer is not alive. If the conditional statement is true, then the logical contrapositive statement is true. If the logical contrapositive statement is false, then the conditional statement itself is also false. They have logical equivalence. If you can find a substitute that tests the logical validity of the statement but not its factual accuracy, you know the claim is not always true and is therefore not logically valid. We need only find one instance, called a counterexample, where the conditions set out in our arguments are not valid. Take, for example, our original statement. If Jennifer is alive, then Jennifer eats food. The converse is, if Jennifer eats food, then Jennifer is alive. The inverse is, if Jennifer is not alive, then Jennifer does not eat food. And the contrapositive is, if Jennifer does not eat food, then Jennifer is not alive. We would need to find a single example of one of these conditions, any one of which would be a counterexample. A living woman who does not eat food, or a woman who eats food but who is not alive, or a non-living woman who eats food, or a woman who does not eat food but who is alive. If we can find even a single example in which the premises are valid but the conclusions are false, we would have a counterexample, showing the original conditional statement is invalid. As you can see, we cannot produce a counterexample for any of our logical statements. Our argument is valid. The logical result of all of this work with converse, inverse, contrapositive, and counterexample logical statements is we learn that Jennifer is a living, breathing woman who eats food.